So thanks for Martin and Mihal for organizing this and for inviting me. So I'll talk about PPSC's algorithm, but before that, so let me make sure. So what can I say about Eric and Mike? So you all said many wonderful things. I will be brief, and they're my treasured colleagues and wonderful people, and congratulations. So okay. I'm going to talk about satisfiability algorithm and in particular PPSC. So you can guess what those letters stand for. That's how it became known. So my goal is kind of twofold. So to convey some of the ideas in the paper, thanks to Mike, and this is an important problem. Maybe I can inspire. This work is done 20 years ago, roughly 20 years ago, up in Seattle, and there is one advancement since then, so that closes the gap. And this is still the last word, and then I would like to inspire you to think about these problems and maybe make progress. And this is not impossible. And okay, so there is this rumor that Mike's papers are the last words on the subject. I think you have to disprove this one. There's plenty of reason to disprove that. Okay, so let me go through the brief introduction. And so we have a formula, a circuit, and n variables. Of course, the number of variables is the complexity parameter here. And we are talking about exponential time algorithms. And it's important to be careful about the complexity parameters. And the goal is to checking whether it's satisfiable. And the standard example is the KCNF. So we can take any kind of circuit, so then ask the satisfiability question. And so basically exhaustive search can solve this problem in this time. And the question is, can we do faster? Can we do faster significantly over exhaustive search? And the parameterization is that, so you can look at 2 to the n to the power 1 minus mu, and mu is called the satisfiability savings, and it can depend on the number n and various other parameters of the formula of the circuit. So what can we say about the savings for the class of KCNF formulas as a function of k and n? Okay. So that's a basic question, and I'm not going to talk about the importance of this problem for complexity reasons and for practical reasons. So let me just mention a couple of words about the history of this problem. Several algorithms and several heuristics have been proposed. This is a very active area for both empirical and theoretical work. And so the algorithms can be, for KCNF, so the algorithms can be broadly classified as DPLL style, and you have a number of important heuristics and local search algorithms. And a variety of analyses have been done for this problem. When the class density is lower, like lowest local lemma can be used to find a satisfying assignment for random formulas. So the list goes on and on. But our focus in this talk will be for general KSAT, and what can we say about the worst case complexity? Okay, so that has been the focus of our work, and so that will be the sole focus, and I will only talk about key results in this regard. Okay. So let me give you a brief history of the worst case lower bounds for KSAT. And beyond the exhaustive search, one of the first results is by Monian and Speckenmeyer, who have shown that they can get a savings of roughly 1 in 2 to the k for KCNF-SAT. Okay. And several years later, so with Powell and Francis, so we have obtained the result. The savings is 1 in k, where k is the width of the case of the clauses. Okay, so the following year up in Seattle, Mike and I were talking about and kind of on how to improve that. That became a very long-term project, and so this is the PPSC result, which is slightly more complicated to explain. So what it is saying is that so the constant of so mu sub k is strictly larger than 1, so that's an improvement over PPZ, and we did not extend that result for all values of k, but from k5 onwards that result holds, and for all k it holds for unique k-sat. And unique k-sat comes naturally into the analysis. I will explain that in a minute. And the value of mu is roughly 1.644. Okay, it's a tiny improvement if you think about it, and it does have consequences in terms of lower bounds. And even the tiny improvement requires a number of new ideas, sophisticated analysis, and that kind of tells you the challenge of this field. And one way you can see this PPZ and PPSC are a way of analyzing the unit class occurrences. What can we say about the occurrence of the of unit clauses, and how can we quantify that so that we can show some improvement in the exhaustive search? Okay. Subsequently, Schoening has come up with a local search algorithm, and that's for each value of k, it is better than PPZ, and it is worse than PPSC for k 5 or more. And subsequently, TIMO has improved, basically has closed the gap, and has improved the analysis for the general k-sat case using a very nice argument, and it closes the gap. Basically, PPSC bound holds for all values of k, so regardless of the value of k, and so that's the best known bound for k-sat at this point. Okay. So let me give you kind of table. People care about 3-sat and 3-sat and 4-sat, and so these are roughly the results for. So I'm distinguishing between unique k-sat and k-sat, and so I should draw the line more carefully. The general k-sat for k equals 3 and 4 have been improved to be the same as unique k-sat due to TIMO. So therefore, the general k-sat result should also read as 0.386, 0.554. Okay. So basically, 0.386 is the best constant for 3-sat. Okay, for the general 3-sat. Okay, so that's the quick and selective history of the. So one thing is that even for the worst case analysis, number of results have been produced. People have worked on kind of improving these constants for a decade, and people filled in the gaps. But ultimately, the currently standing bounds are those. Okay. Okay. So what my plan is, basically PPSC is an improvement, a significant improvement, both conceptually and analytically, so over PPZ. And so my goal is to kind of to explain some of the ideas in PPSC. So PPZ will serve as a baseline to see what new ideas are needed and how they kind of enable the improvement. Okay, so let me give a very quick summary. Okay, so the idea is that so this is basically a DPLL style algorithm. So you take a KCNF and you take a random permutation of variables. So you examine the variables one at a time. If there is a unit class for that variable, so you set that variable according to the unit class. And if not, set the variable to either 0 or 1 randomly with uniform probability. So that is simply the PPZ algorithm, which is a small variation of DPLL style algorithm where we permute the variables. Okay. So that's basically what it says. It looks for a unit class, and if it is there, we can set its value. So we can force its value, because that's the only way the formula can be satisfied. And if not, we set it randomly and simplify the formula to repeat this operation. Okay.
I suspect that not everyone knows what the phrase unit class means.
Okay. So good point. So KCNF, you have clauses. The clauses can have width up to k. So unit class is a class with width exactly 1. So therefore, for the formula to be true, the variable or the literal in the unit class must be true. So we can set it without having to guess it. So that comes for free, basically. So the idea is that if you have to guess every variable, the probability of guessing a satisfying assignment is no better than 2 to the minus n. Of course, assuming you only have one satisfying solution. Okay.
Let's do this for loop once.
Pardon?
Let's do the for loop once.
Well, if you wind up with an empty clause, you abort, because you're not going to satisfy it.
Right.
Yes. Would you wind up with an empty clause? Quick.
So-
No set variable.
So towards the end, if you have an empty clause, of course, f is not satisfied, you don't output anything.
Yeah.
So we only run it once. So this is a probabilistic algorithm that runs in polynomial
I
time.
see. So if it doesn't finish, if it finishes, you're done.
Yeah, if you output an assignment, it's correct, but if you got to show the chance of doing that is more than zero.
So the point is that once you quit the loop, all variables are set in some fashion or other. So you look at the resulting formula and see if it is satisfied or not. Okay, so this is the basic algorithm. So the only innovation is that we are looking at the variables in a random order, and so the improvement over exhaustive search comes when we encounter a number of unit clauses. Okay, so now the key goal is to see whether we can estimate the number of unit clauses, and a priori it's not clear why there should be unit clauses or several unit clauses that should appear in this, of course, in this iteration, and the k plays an important role. So the low width of the clauses plays an important role in this calculation. So let me quickly show you the argument. So both for PPZ and PPSC, so the kind of analysis bifurcates. We focus on the case when the formula has exactly one solution, or more generally when the formula has one isolated solution. Of course, a solution is isolated when none of its distance one neighbors are solutions. So you have the solution, kind of you look at the Hamming distance one neighbors, they are not solutions. Okay, and it's not. And it may not be particularly surprising if you look at the results. So unique SAT may be the hardest so unique SAT instances are among the hardest instances. If we can tackle them, so there's hope that we can generalize. So that's how it turns out to be. And so this explanation comes as an after fact, but this is how we started thinking about it. Okay, so let's assume you have an isolated solution, and so let's focus on one of them. There could be several such isolated solutions, and an interesting question is that how many such isolated solutions can be there for a KCNF. So if you can, of course, this algorithm will answer that question. That in turn can be used to prove a very precise lower bound on parity for depth 3 sigma pi sigma circuits. So we're not going to go into lower bounds in this talk. I just want to mention it once.
Probability of success is still going to be very low, but if we show that it's 2 to the minus 0.9n, we get
right. Yes, I will show that in a second. So think of these algorithms as a probabilistic polynomial time with success probability slightly better than 2 to the minus n.
Yeah.
And how much better they are with respect to 2 to the minus n, that determines the savings. So then we repeat this algorithm multiple times, or 1 in the probability times, so to get sufficient certainty that will output a satisfying solution if 1 exists. Okay, so that's the paradigm, okay, so we focus on a particular isolated solution. So now the thing is that if we can, so you want to understand when unit clauses are going to occur during the DPLL style algorithm, so clearly there are. So the concept of an isolated solution is a semantic concept. It's a concept of the solution space. So somehow you want to learn something about this isolated solution through the clauses. Okay. So it turns out there's a natural connection between the clauses and the isolated solution. And so take the formula and fix one isolated solution. And without loss of generality, assume that solution is all ones. Plug it into the formula. The formula must be true because it's a solution. Since it's an isolated solution, for every variable, there must be at least one clause with that variable appears as 1, and the rest of the literals in the clause are 0. Okay, and okay, so this is so let me give you the outline first. Sorry, so then I will tell you the details. So the idea is that we want to lower bound the probability that a variable appears as a unit clause. and that lower bound will be 1 in k. So from that we can easily infer, because an average or with a sufficiently high probability, 1 in k fraction of the variables appear as unit variables. So therefore we have a savings of 1 in k fraction. So 1 in k fraction variables, we don't have to randomly guess them. So that gives the advantage.
Is this an independence assumption?
No, we don't need to.
Because what happens if you only see unique variables in the case that you've already blown the formula?
So you will see. So that's the reason. So the probability that the number of that's the argument. That's a simple Markov inequality. So there's no deep. Okay. So then we conclude that for an isolated solution that it is output with probability at least that 1 in n comes because of the Markov's inequality. Okay. So basically this shows that we have a better than exhaustive search probability for outputting it, provided we can show that a variable will appear as a unit class. Okay. So let me, of course, this only tackles the case of one isolated solution. So if there are many solutions, okay, we generalize the notion of isolation to a degree of isolation, and then we sum the probabilities over all solutions. So either you have a lot of solutions with maybe small isolation for each, or you only have one solution with a large isolation. So the degree of isolation means the number of neighbors which are non-solutions. So this dichotomy holds. So either way we get the right probabilities. So that's the sketch of the argument for PPC. So let me explain one of the key detail, and so that's the definition of the isolated solution and the degree of isolation. So this is what I was saying before. There must be at least one clause basically at an isolated solution such that that clause is minimally true. And for each variable at the isolated solution, there is one clause which we call critical clause that is minimally true. That particular variable is set to be true. And of course, all the literals in that clause are set to 0. Okay. So that's an interesting clause, and what happens is that, so let us say in the random permutation, that all the other, so take a variable, take its critical, and take one of its critical clauses. So let's assume in the random permutation that variable appears as the last variable among the variables in that class. So and assume the other variables in the class are set to the correct values as per the solution. So by the time we get to this variable must appear as a unit class. Because if you are setting the variables according to the isolated solution, then all the other variables are set to 0. So this variable, so the variable in question will appear as a unit class. So we get to set it for free. Okay. So let me repeat this argument. Let me go through this argument more slowly. So we fix one critical clause for each variable at the isolated solution, and the probability that a variable appears as the last variable in its critical clause is at least 1 in k.
I guess I don't know if I want to say it out too much.
Okay. Sure. Go ahead.
And this argument that there has to be a critical clause for each variable.
Okay. So let's take an isolated solution. So plug that into the formula. So the formula, of course, every clause in the formula must be true.
Right.
Okay. And I claim for each variable there must be one clause that is minimally true. Because if not, so you can flip that variable, and the formula is still satisfied. So that means if each clause has at least 2 ones in it, by flipping one variable, so you can still make each clause true. So therefore, so there must be some minimally true clauses. Minimally true means there's exactly one literal that is true. So
I got it.
Okay. So okay. So therefore, if you take a random permutation, that this variable will appear as the last variable among the variables in the critical clause is at least 1 in k. And so from that we can conclude on average n over k variables will be forced in a particular execution. So then we can use the standard probability arguments to conclude that PPZ will output this particular solution, this particular isolated solution. So I have generalized this. So let X be a solution with a degree of isolation of I of X, and that's the probability of outputting that. Okay. So the argument is pretty simple, and so let's look at two events. One event is that 1 in k fraction of the variables do appear as the last variable in the critical class. And so E2 is that the remaining variables, of all the variables are assigned according to this isolated solution. Okay. So the probability of E1 through Markov's inequality is 1 in n. And given that E1, probability of E2 is basically 2 to the minus n plus the number of unit classes. Okay. So that will give you the probability. So now to generalize it for a general case, and so we make a simple observation. So let S be the solution set of a formula. I assume that S is non-empty. So let's define the value for each solution of the formula. Let's define the value, which is 2 to the minus n plus the degree of its isolation in the space of solutions. And the simple combinatorics tells us some kind of, so if you look at the perimeter of the solution space, that cannot be too small. Okay, so that's the kind of situation, that kind of fact shows, combinatorial fact shows that some of the values must be at least 1. Okay, so then using this fact, we can argue that one solution will be output by PPZ is the sum of the probabilities. Or since each solution is distinct, each event is distinct, you can simply sum the probabilities. And so if you factor them out appropriately, so you will see it is basically so 2 to the minus n plus n over k. Okay, so if you repeat this algorithm several times, with constant probability, you will output a satisfying solution. Question?
So is the conclusion that there's a randomized algorithm, or can you de-randomize and get a deterministic algorithm that runs this time?
So there are de-randomizations that achieve the same bound.
Okay.
Right. I'm going to confine myself to randomized algorithms. And if you kind of one-sided randomized algorithms, if you repeat them sufficiently many times, you get constant probability. And so the probability of success is what matters here. Question?
What if a solution does not have any isolation degree?
So that's the so that means there must be many solutions. Okay. So think of a solution space where no solution has isolation greater than 0. That means every point must be a solution. Therefore, 2 to the minus n summed over all solutions is 1. So that's an extreme case. And if you have even one non-solution, the solution that's close to that will have many non-solutions next to it. So the degree of isolation will be non-zero. So if you take all these so things here, so that lemma, so that bullet 3 kind of sums it up, saying that that the value of overall solutions, whether it's a sparse set or a dense set, so the value will be at least 1. So for example, it will be optimized when you have parity. For parity function, let's assume the solution space parity function, and so that I believe that's maximized in that case. Okay. So let me quickly move on. So this is the quick summary, and so the summary is that we are focusing on, we are looking at unique satisfying solution, the case of unique satisfying or somewhat isolated satisfying solution case. And we are looking at the event that variables appear, so that variables are forced in this process. And if we can lower bound the probability of forcing, so then we can use standard probability arguments to improve the probability of success. So that's the high-level argument. The PPZ shows that you can lower bound the forcing probability to be 1 in k. And so where do we go from here? And so we want to improve this. And so let's look at some ideas on how to improve this. Okay. So one idea would be that maybe there are more critical clauses per variable somehow. And so let's look at a case. So let's assume that the solution is all ones. Can assume it's isolated, and let's assume it has two critical clauses. Of course, x1 will be forced provided it appears after x2 and x3 or after x4 and x5. So the probability of it being forced has increased now. So if you do the calculations carefully, so the probability of forcing before, when you only consider one critical clause, the probability of forcing is 1 in 3. And now that you have two critical clauses without overlap for the same variable, so you have a probability of forcing of 7/15. Okay, so that's an improvement. And if we can make sure that every variable has two distinct critical clauses without further overlap, except that variable will appear, so then we have an improved algorithm. Okay, but there's no way we can guarantee. Of course, in general, there are formulas. So even if it's a unique solution, there's exactly one critical clause per variable. So we can't bank on the fact that we'll have a copious number of critical clauses. Okay, so that doesn't quite work. So let's look at the next idea. Okay, so we don't have two critical clauses for x1, but we have we have two critical clauses, one for x1 and one for x2. So assume that, of course, the solution is isolated for now. And so now you can apply resolution. So that's a new idea. Okay, so you can get another critical clause for x1 of length 4, of width 4. And of course, it does have some overlap with the original critical clause. So now you can say that x1 is forced provided it appears after x2 or x3 in the random permutation, or provided it appears after after variables 3, 4, and 5. So you can now do whatever inclusion, exclusion, whatever, you can now figure out the probability, so that will be better than 1 in 3. Okay, so that looks good. So we can kind of play one critical clause against another critical clause, and hopefully we can derive more critical clauses. Then we can use those critical clauses to improve our forcing probability. Okay, but the problem is that such a situation may not happen. Okay, so for example, look at the critical clause for x2 might include x1 complement. Then the resolution between those two clauses will not produce anything useful. So we could not get a new critical clause for x1. And it's not particularly surprising that if there is so remember, we are thinking that all ones is a solution. So let us say that there is another solution at distance 2 from that. That means 0, 0, and 1 to the kind of n minus 2 is also a solution. So then every critical clause for x1 must necessarily include x2 complement. Similarly, x3 complement. So that means if that were the fact, then we could not produce a critical clause for x1 through resolution that would not include x2 and x3. So therefore, all the critical clause will produce will be longer ones, and they will not produce any new information. Okay, so this is not enough. Okay, so we need one more idea. So why not, and why don't we assume the solutions are not only isolated, but they're de-isolated. So look at the Hamming neighborhood of distance d. So let's assume for now that there are no solutions in that Hamming neighborhood of d. Okay, so there's a kind of intuition guiding that maybe the unique SAT is the hardest case. So let's tackle that regardless of the consequences. So regardless of the generalization. So that's the belief that so we are focusing on this one. Okay, so the next assumption we are making is that we have solutions which are de-isolated. D will be a slowly growing function of n. Okay. So now this distance 2 neighbor is not a satisfying solution. It's because of the assumption. And now we can conclude there must be one more critical clause for x1 that gives some extra information compared to the critical clause we started with. So for example, that if you flip both x1 and x2, the formula must be false. And that falseness must be witnessed by some clause in the formula. And without loss of generality, assume that clause is x1 or x2 or x4 bar. Because that clause, which is falsified as a result of flipping both x1 and x2, must include either x1 or x2 or both. So let's take one of the cases. Of course, the other cases are not significantly different. Now you can do the resolution. So get a new clause, basically x1 or x3 complement or x4 complement. So this is a critical clause for x1, of course, at the same solution, and it is distinct, and it improves our forcing probability because this is different from the critical clause we started with, which is x1 or x2 complement or x3 complement. Okay, so now we can do our calculations, and so we can improve the probability of forcing. So using this kind of argument, you can see we might be able to produce through resolution and through the idea of de-isolation, or de-isolation, that we may be able to produce a lot of critical clauses. Okay. So these are the two important ideas to develop the algorithm. So let me quickly give you the algorithm. So what we do is that you do this S-bounded resolution, as long as the clauses are bounded by S. So then you resolve them, and so let F sub S be the closure under this S-bounded resolution. So you take this new formula, and we apply the same algorithm PPZ for this. So this is the PPSC algorithm. So we are doing a pre-processing, apply resolution, polynomial, roughly polynomial amount of time. So that's enough, and for a sufficiently large S, and so we have the new algorithm. Okay. So now becomes, okay, now there's a new challenge here. So the new challenge is that how do we analyze this? Okay. So we do know, through the examples I demonstrated, that we do know that these two properties, resolution and de-isolation, do guarantee multiple critical clauses. Okay, for each variable at a given, of course, at a given de-isolated solution. The problem is that these clauses have varying lengths, and almost unknowable can overlaps with each other. So we don't have much information about the formula. We apply resolution blindly, and we get lots of critical clauses, and PPZ does take advantage of them. But to be able to analyze that algorithm, so we need to have some control over the kind of overlapping patterns of these clauses. So this is a gigantic problem. Okay, so this is not an easy problem. So even when you have 3 or 4 critical clauses, so basically computing the probability of forcing is not that trivial. So you have to go through detailed calculations. Okay, so this is in fact very messy. Okay, so if anyone has some nice idea to do this, let me know. And so this is where there's a big pause. Okay. So let me tell you the next important idea, and so we have this new concept called critical clause tree. Okay, so I will explain this slowly. Okay, so let's take a de-isolated solution, so the general idea is that rather than applying resolution, of course, in the algorithm we first apply resolution, apply PPZ. But for the analysis, okay, we want to generate, and we want to control the generation of these clauses in such a way we can have some structure on the clauses. So we are going to select a subset of these generated clauses, so that they become a structured object, and we can calculate the forcing probability more easily. So that means we are going to leverage the generating process and look at a specialized generator process. So we have this notion of a critical clause tree. And what it is at a high level is that it's an indirect and a controlled method of generating critical clauses for the variable, of course, at a given solution. Applying resolution blindly gives you lots of critical clauses, but we can't understand them, so we don't have control over them. So we come up with another procedure for the sake of analysis only to generate the critical clauses. And that concept is called the So the critical class tree, this is clearly the most important concept for the analysis. And without this, it's kind of, and it's quite unwieldy, we have no idea on how to proceed. Okay, so let me tell you what this is. It's a rooted tree, and each node is labeled or unlabeled, and the root is labeled by the variable in question. Okay, we build a critical class tree for each variable. Okay, and some of the leaves might be unlabeled, so you will see why they are unlabeled in a second. And one important property is that the labels along a root to leaf path must be distinct. No variable can repeat. Okay. And finally, the most important property, this is where the resolution comes into picture, is that so if you take any cut of the tree, by that I mean it's a set of nodes that that does not include the root, but it separates the root from the leaves, from all the leaves. So cut is a set of nodes, not including the root, that separates the root from all the leaves. Okay, so if you take any cut, that cut essentially gives you a that cut essentially gives you a critical class. So for every cut, so there's a critical class that includes some of the variables in that cut and the variable in question. Okay, so of course I kind of ignored some of the parameters here. So what happens is that there's a connection between S-bounded resolution and the depth of the tree. Okay, when we do S-bounded resolution, so we can develop a tree with this property up to depth d. And if a node is unlabeled, there's no label for that, so the corresponding set of variables gets to be smaller. Okay, so this is the important property in the sense we can generate the clauses. So the needed clauses, which are the critical clauses, as of course as the cuts of a tree. So we are going to simulate or mimic the resolution by building this tree. So the building of this tree is a way of understanding the resolution process for our purpose. I will explain the construction of the tree in a minute. So once we have a tree with these properties, the calculation becomes easy. Okay, so let me explain the calculation. So let's take a critical class tree and assume we have built it up to depth d. D is the isolation we need, and assume without loss of generality that the solution is 1 to the n. And so this is one thing to note is that I haven't described the construction of the tree. One of the properties of this tree will be that the number of children for each node will be bounded by k minus 1. Okay, so let's look at the root and sorry for the typo. Let's look at the k minus 1 children of the root I. Okay, and let t1 through tk minus 1 be the respective subtrees rooted at those children. Okay, so now my goal is to analyze somehow the cut probabilities. I'll explain that in a second. So we need one more concept dealing with these random permutations is very complicated, and there's a kind of very nice trick of replacing the random permutations with the random placements. So let alpha be a random placement, basically that assigns to each variable some real number between 0 and 1. Okay, so this is isomorphic distribution, and this is an equivalent distribution to random permutations. So that's what we will live with. Okay, so what we are interested in is that we want to compute that the variable I is forced under random placements. Okay, that probability is at least that the variable of I is placed after the variables in some cut of t, because the cut of t basically defines the critical class. So therefore, if I appears after all the variables in a cut, so that means I must be forced. So the probability basically, okay, we have this existential quantifier there. Of course, I can appear after any cut of t, and that's a good event. So you want to now determine the probabilities of the union of all these events. Okay, and because of the nice structure we have for the critical clauses, this probability is a lot more. So the computation of this probability is a lot more tractable. Okay, so let's look at, so let's assume that R is so let's do the conditional calculation here. Let R is the placement for the variable I. So we have some real number R, so that's where I is placed in the line between 0 and 1. Okay, so that means I is forced if for each child. So either that the variable that's labeled at the with the label at the child appears before the variable I, or if you look at the subtree rooted at the child, that the variable at the root, which is I, will appear after some cut of the subtree. So if one of these events is true for every child, so that implies that the variable, which is the root variable, appears after some cut of t. Okay, so if you look at the disjunction in this product, and so those two events are disjoint, so we can simply sum up the probabilities. And if you look at the second, event in the disjunction, and it turns out they're independent because the fact that the root of a subtree is placed at some point, basically at some point, has no bearing on the rest of the variables in the tree, because each path in the tree has distinct variables. So the root has basically information about the root, so it does not bias us regarding the placements of the variables in the subtree. So therefore, we can take that, and we can take the product of the two probabilities because of independence. So then we have this outer product. So it turns out, of course, I convert, strictly speaking, it's an AND of the probabilities. And these probabilities happen to be correlated, or these events happen to be correlated. So using some using some standard correlation inequalities, we can convert the AND of correlated events, the probability of AND of correlated events, and lower bound it by the product of probabilities. So now we have a nice recursion here. And of course, in each step of the recursion, the depth of the tree decreases. And calculating this probability, so this probability is not that complicated, it is still involved. So this gives a handle on the whole process. Okay, now we can evaluate this. Okay, so this is what I mean by generating the critical clauses in a controlled fashion, so that we can estimate this probability. So the fact we need is that the cuts of the tree correspond to critical clauses. So then we have a nice recursion here. Okay. So the last idea that we need is that how do we construct the critical class tree? Okay. So it's a simple process. Let me explain. So we start with a variable I, label the root with that variable. So this is the general rule. So take any, of course, you have constructed a tree up to some depth, and take any root to leaf path in the tree, and it all has distinct variables. Flip all the variables. Of course, your reference point is 1 to the n, which is the de-isolated solution. Okay, now you flipped up to d variables. Since it's a de-isolated solution, the formula must be false. So there must be some clause in the original formula that's falsified. Okay, and some of the variables you flipped will appear in that formula, and some variables don't appear, perhaps. Okay, so this is how you extend the tree. So you take, so there's a false clause, and you take the variables which do not already appear along the path, so then add them as children to the leaf of this path. Now you have grown the tree by up to k minus 1 children, and so you have, of course, you have a deeper tree. So the deeper the tree is, the better, because you have this recursion up there. So that adds more values as the tree depth increases. And to the extent we can guarantee, so there's another, of course, else clause. If there is no such variable, that means if all the variables in that clause already appear in the path, so then have a child with no label. So that means certain coincidences happened. So we have a shorter resolution. So we don't really need to extend. And a no label leaf is a good leaf. Okay, we don't need to extend it any further. So with induction, we can prove that this tree satisfies the cut property. So take any cut in the tree, there is a corresponding critical class. Okay, So this fact, so the only fact we are using is a de-isolation. Okay, of course, in proving that the tree satisfies the cut property, we are applying resolution, and you can do a straightforward induction to prove the property. Of course, induction on the depth of the tree. So just to give you the idea, to get the tree started, so there must be at least one critical class for the variable because of the de-isolation. So the first off, you take the variable, and there are k minus 1 other variables in the critical class. They will become the children of the root. So you built it up one, so then you take a root to leaf path, flip 2 variables. There must be some other class that's falsified. So there will be some more children will happen, and so on. So this process must keep going on until the time when you either get a leaf with no label or you exceed the depth d. So in either case, you built a deep enough critical class tree, and so this is a summary of all the ideas, and the summary of the analysis. So we construct the critical class tree, and the cuts correspond to critical class. So then we calculate the probability of forcing, and so using a recurrence relation. So that gives you the basic theorem that for de-isolated solutions, the probability of forcing has improved, and mu sub k is roughly 64. And so you can see the improvement is tiny. So nevertheless, it's an improvement, and constant factor improvement. And so mu sub k is an interesting series. And so the limit value of mu sub k is pi square over 6. And so those are the facts. And so I only have a couple of more slides, and so this will help us prove lower bounds. So that fact will help us prove lower bounds. So let's not go into lower bounds. So now the only remaining question is that how do we generalize this from de-isolated solutions? So what if the formula does not have any de-isolated solutions, okay, for sufficiently large d? So then we had to use we used a somewhat involved, very complicated argument to be able to extend it for the general case. And we did, for k greater than or equal to 5, we were able to extend and obtain the same upper bound as that of unique SAT. And subsequently, so Timo has come up with a nice analysis for this extension and simplified the proof. So we can now say for all k, the probability for any general KCNF, PPSC succeeds with that probability. Okay. So that completes the theorem or the basics. Okay. So let me take one slide to talk about open problems. So basically, as I was saying, people use a lot of heuristics successfully in SAT solvers. And there is tremendous success. If you want to be challenged by SAT solvers, please talk to Moshe Vardi. And he believes complexity theory is useless because SAT solvers solve all the problems. So therefore, one of the kind of obligations of the theoreticians is to understand kind of why these heuristics work in practice, and do they really work for worst case instances. And so to some extent, we succeeded with the unit clause analysis, and there are a number of very effective, seemingly effective heuristics like clause learning. Okay, can we extend these analysis to deal with other heuristics? That will be of tremendous practical and social interest and theoretical interest. Or one can come up with completely new algorithms with improved bounds. Okay. For the complexity theories, so let me pose one open question. Russell and I have thought about it, but we don't think that that doesn't mean that that we have hit the kind of road, that we have hit the kind of the final word on this story. We encourage you to think about this problem. So let me define this. So this constant S sub k to be the optimal exponent for solving KCNF. Okay. Let's have two hypotheses. ETH that says, of course, S sub 3 is bounded away from 0. strong ETH says that the limit of these constants is 1. Okay, there is some background behind them, so let's not worry about it. So the question is that, so given that people have spent multiple decades trying to improve SAT algorithms, K-SAT algorithms, and the best constant at this point for the worst case is 0.386, can we at least prove a constant lower bound, assuming ETH or strong ETH, or both? Of course, one implies the other. So that will be a very nice theoretical result, and that at least shows that that we have a concrete constant that we can't go beyond it unless ETH is false. So kind of one obstacle for doing this is a kind of familiar obstacle. We know, so the only reduction we know to go from 4-SAT to 3-SAT. See, one way of doing this is that by finding the right kind of reductions to go from 4-SAT to 3-SAT. So the only reductions we know is that by introducing lots of new variables. So even for sparse formulas, you need to introduce lots of new variables, linearly many, so new variables that kills all the constants. So we need a different kind of trade-off, reductions that trade off clause width for the number of variables or some other complexity parameter. So if we can come up with a nice reduction from 4CNF to 3CNF, the last result, one might be able to prove the last result assuming strong ETH is true. And if such a reduction is not possible, finding reasons for the impossibility of such reductions will be useful as well. Okay, thank you.
Questions?
We know that PPSC or PPZ does not do better than this claimed one, than what the theorem says.
People have found almost matching counter. People have found counter examples where the analysis is tight.
Okay.
Of course, in practice, I don't know, because in practice, they seem to perform well. Of course, the SAT solvers perform well on some classes of examples. So theoretically, this analysis cannot be improved up to constant factors.
Have you ever tried to mix Schoening's technique with this? Give any advantage?
What's the
I
question?
did try particular.
If you take
So
if
the
you take
question is
this,
that
can you mix this with Schoening's to use this to find a solution and then try to fix it?
Can we hybridize the local search techniques with the DPLL style? So if you look at the development, so PPZ gave somewhat better bounds compared to the previous algorithms,
right.
but the local search gave much better bounds than PPZ. Of course, PPSC has beaten both. So
But maybe you combine them.
So what happened is that the case for k equals 3, PPSC did not improve the bound of Schoening because we had a gap in our analysis, while our unique SAT bound is 0.386 that beats Schoening's bound. So the general 3 SAT we did not, and we could not match Schoening's bound. So of course, in between, and that happened when Timo has successfully extended our result to k equals 3. Of course, in between, people had tried to hybridize both the techniques, did improve on Schoening's result, but no one has been able to improve the unique k-SAT result.
Okay.
So that Timo has tried. So he has some result that might apply for the 3 SAT case, for unique 3 SAT case, and where the improvement is really, really small. Maybe in the 10th decimal.
I have a question. So is there some could you get an improvement by actually not taking very broad random, but actually taking some small clauses, which once you have some small clauses, then you actually take in the...
I mean, that's one of the nice heuristics, and I don't know how to analyze that one. So Russell believes that it is our tools for so the lack of tools for analysis is the problem, and perhaps many of these ideas are like looking at the variables in the short clause, and there are more sophisticated techniques for selecting variables and clause learning. They might in fact improve the improvement, but we don't know how to analyze it. So there's a question here. We may have a good algorithm, so that beats PPSC. Well, we never know. So the existing ones might beat it. So clause learning is in fact very tantalizing. So that's kind of is producing more critical clauses in a more intelligent fashion. And it's not clear how to analyze that. So that's worth taking a shot at.
If there are no more questions, so let me actually thank all the speakers.